Hey everyone, how's it going? Well done as always for getting yourself to do physics on a Sunday. Yeah, how are we doing? So today's session is on wave-particle duality, which is a really nice topic actually. It's quite a conceptual one. So kind of as the title suggests, we're going to be talking about, when we say duality, we mean a kind of equivalent. So we're going to be talking about how waves and particles are in some way the same thing, or are at least in some way quite similar. Like you can talk about things like frequencies and wavelengths of particles, and you can talk about certain particle-like properties of waves. So it's actually quite surprising stuff, and we're going to cover quite a lot of that today. So that's going to be great. So we'll start off in a couple of minutes. In the meantime, have people seen this topic before, or is this totally fresh? Hey, how's it going? Hello from England. I should have been able to think of that quicker. So if you're wondering with exam boards today, so what we're doing is covered in the main, at least the main 3 exam boards for UK levels. So OCR, A-level, OCR, AQA, and EdXL. Yeah, I'm good, thanks, actually. I'm feeling very chilled out this weekend. Hung out with a couple of friends yesterday for one of their birthdays, but otherwise I've done pretty much nothing. Cleaned the house a bit, so it's been pretty relaxed. I kind of wanted to go for a run today, but I haven't gone for long enough that I know it's going to be really hard. You actually, how are you getting on with it? If you have any questions, you'll probably have some quite decent chances to ask about them. Yeah, so I should mention that actually when I'm doing the session, like do feel free to ask any questions you have in the chat. I'll probably ask you some questions as you go along as well, just to check it's all making sense. But yeah, do stop me if you're confused about anything. Interesting. Okay, my suspicion is that it's at the same point naturally for one of the exam boards. Then maybe you're both doing the same exam board, because that can kind of change which order you see this stuff in. Okay. Hey, how's it going? Right, let's get the show on the road. We've got plenty to go through, so let's not waste any time. As I said, let me know if you have any questions, and let's get started. So today is on wave-particle duality, but just first quickly, so you know a bit about us. So we're SnapRevise, and I am Matt W. So I'm head of physics here at SnapRevise, and kind of alongside that, I'm also a PhD student in physics at Oxford. I'm actually in the computer science department, but I spend most of my time thinking about physics. And yeah, I've been tutoring A-level physics for the last 4 years or so. Hey, Sachin, how's it going? All right. So just so you know, today there is an offer So if you like what we're doing here today, and you're interested in seeing what we're doing on the Satirise website, then we've got a New Year offer here, back to school offer. So it's 25% off a first month subscription. So you can use this code on our website and get 25% off your first go. Yeah. So for now, let's do some physics. So our objectives today are threefold. We want to understand how light and electrons can behave essentially both as particles as waves. So we usually think of light as being a wave, but it has some particle-like properties. And we usually think of electrons as particles, but actually we're going to discover they have some wave-like properties. So I would say atoms are made, roughly speaking, of three things: protons, electrons, and neutrons. Although if you do second year A-level physics, you'll see that protons and neutrons are also made of even smaller stuff called quarks. Past that, I'm not really sure. Okay, so there is some stuff that we're going to want to know that will help us get through today's session. Essentially, just a couple of things that would be good to know about waves. So I'm going to start by reviewing the electromagnetic spectrum. I'm just going to have to change something here quick. Let me check this. Yeah, good, that's working now. Okay, so let's assume that on the left-hand side here, I'm looking at the low frequency end of the electromagnetic spectrum. And on the other end, I'm looking at the high frequency part. Let me write that in. Then what are the names for the electromagnetic waves that we see on the lowest end, the lowest frequency end of the electromagnetic spectrum? And while you're at it, what kind of names do we give for the waves at the high end? So let's call this question 1. Question 2 is, what do we have at the high end? And question 3, what, as far as we're concerned, is kind of in the middle. So there's all these different types of electromagnetic waves. Good. So for number 1, I would say, yeah, radio waves. Perfect. And I should mention low frequency also means high wavelength. Yeah, so in the middle, just down here, we've got IR, that is infrared, absolutely right. Any ideas for number 2 and 3? So number 2, the kind of highest frequency waves. Good, so for number 2, I'm going to put gamma. Those are the highest frequency. And in the middle, I mean, the middle is kind of more subjective. You're right. So actually, I would call these microwaves here because they're in between infrared and radio. Right in the middle here is what we're going to be taking to be visible light, if you like. Here we've got UV, that's ultraviolet. And here, just to complete the picture, X-rays. So the point is, there's all these things on the electromagnetic spectrum. We usually think of them as waves. And we have gamma at one end and radio at the other. Good. Okay. So let's say I tell you the frequency and the wavelength of a wave. How do I know what the speed of the wave is? Is there a formula that gives me the speed of the wave? And furthermore, what is the specific speed given for the speed of light? So let's call this question 1 and question 2. Question 1, what's the general formula for the speed of a wave? Question 2, what's the speed of an electromagnetic wave like light? Good. So the general speed of a wave is given by frequency times wavelength. And altogether, the units there being speed are going to be meters per second. And then what is the speed of light, of visible light, of gamma rays, of radio waves? Assuming we're in some kind of a vacuum or something pretty empty. Good. It is 3 times 10 to the power 8 meters per second. This is stuff that's definitely going to be useful to know today. Good. Okay. Finally, kind of a separate thing, because so far we're talking about light, waves and stuff. Now we're going to talk a bit about particles and a bit about energy. So we're going to define a special unit called the unit of electron volts, which is essentially much more handy than joules for when you want to talk about the energy of a single particle. So 1 electron volt is given by, and I'll write the definition here, the work done when 1 electron moves through 1 volt. So to see why there would be work done when you move through a potential difference, an electron through a potential difference, it's worth knowing kind of one, what is the formula for work done in terms of potential difference? And then 2, what will that give us for the size of 1 electron volt in joules? So how do I find work done if I know charge and I know potential difference? I'll give you a hint that often actually, if you look back at your textbooks, voltage is usually defined as energy per charge. So that's a hint. Okay, so it's good. Yeah, perfect. So work done is given by the voltage times the charge, the potential difference times the charge. So here, good, really nice. Here we've got 1 volt and 1 electron going through. So 1 electron volt is just going to be the charge of an electron times 1 for 1 volt. And the charge of an electron is 1.6 times 10 to the minus 19. So 1 electron volt is 1.6 times 10 to the minus 19 joules. Perfect, really good stuff, well done. So in terms of the spec points that we're going through today for the various major exam boards, here's the stuff we're going through for AQA. There's kind of 2 key equations here, I would say. This one here and this one here. You can see both of these popping up for OCR as well, and also similarly for Edexcel. Okay, perfect. So the first thing we're going to do is look at something that we usually consider to be a wave, which is light. We just talked about the spectrum of light. We talked about frequencies and wavelengths of light. And we're going to see that sometimes light can be treated as a particle, or ought to be thought of as made up of a beam of particles. So there's a classic experiment that was used to essentially discover this fact. And the experiment starts as follows. So we start by taking what looks like quite a strange piece of apparatus, okay? So we've got stuff here which is largely made of metal, some kind of metal. I don't actually remember which metal it was. And here we have a particularly thin piece of metal, typically taken to be a gold leaf. So you might have seen something like a gold leaf before. The point is it's a very light and kind of flappy piece of metal. So in this experiment, what was done was people put an electrostatic charge on this chunk of metal. So there's a load of extra negative charge hanging around on this piece of metal. Okay, so it's currently charged. And that is why you can see this metal here essentially lifted up a bit. The point is it is being repelled by the negative charge on the rest of the piece of metal here. Was it brass? Nice. Okay, so remember here that like charges repel. So that's what's happening here. Okay, good. So now something quite wild happened. People decided to imagine, and actually did, take some light and shine it on this piece of metal here. And they decided to observe what would happen. And can anyone tell me, for certain frequencies of light, what happened to this gold leaf? So something happened to this gold leaf. It's currently raised up. It's currently being repelled by this by the fact that there's negative charge on the leaf and on the piece of brass. And then something changes when we shine light on the piece of metal. Certainly, so that will absolutely be our explanation for what happened. What the experimenters first observed was simply they were just looking at this piece of metal, and what they observed was that the gold leaf moved. In particular, towards the rest of the metal. So the gold leaf moved like this, back down to here a bit. Exactly, so it fell down. That's a nicer way of phrasing it, actually. Yeah, it fell down. Why? Absolutely right. So we kind of, what was then inferred from this is that, well, what was causing this repulsion was, it was electrostatic repulsion. So if we could get rid of some of the charge of the bit of metal, then the gold leaf would fall. There'd be less repulsive forces. And so that's what we kind of, that's what the people doing the experiment decided. They said, okay, negative charge must have been lost. This is because light was knocking electrons away from the metal. So what's weird is that this only actually worked for certain frequencies. So it certainly is the case that these electrons were essentially kicked off of the metal, and that's why the gold leaf fell. What's surprising is this didn't work for all frequencies. It worked for blue and ultraviolet, things like that, but it didn't work for red and infrared light. So below a certain threshold frequency, this effect did not occur. So now we need to explain why, if we have light that has too low of a frequency, this effect doesn't occur at all, not even if you shine the light there for ages. And the deduction that was made from this is that essentially light must be made of discrete bits, with the energy of the bits depending on the frequency. Why does the light knock the electrons off? So essentially the idea is that the light has energy, and that the light is giving the electrons enough energy to escape the metal. So maybe they're attracted because of all the protons that are attracting the electrons towards them in the metal. But the light gives them enough energy to escape. However, below a certain frequency, even though the light should still be giving them energy, it never, ever, ever gives an electron enough energy to leave the plate. And that tells us there's something kind of uncontinuous going on. So the deduction that was made, second, let me check, good, was that light travels in discrete packets. Okay, called photons, with energy depending on frequency. So the idea is, if I have a beam of light, but each one of them has each particle in this beam of light doesn't have enough energy to knock off an electron, then no beam of these particles is ever going to give one of these electrons enough energy to be knocked off. So that's the idea. Okay, so it turns out that you can actually find a formula that relates the energy of each of these particles to the frequency. And it's given by the following. Energy is given by H multiplied by F. So F here is the frequency, but what's the name of this H thing? Energy, of course, being measured in joules, frequency being measured in hertz. This H here was called Planck's constant. Okay, we won't write that down. Good, Planck's constant, absolutely right. And another way of writing this then was hc over lambda. Why? Because frequency is given by speed of a wave divided by wavelength. Okay, so this brought in a new important definition, which is the definition of the work function. So the work function of the surface of a metal was defined to be the minimum energy a photon needs to have to liberate. Liberate is just a fancy word for knock off, as I was saying before. So the minimum energy a photon needs to liberate an electron. Good, okay. Yes, and I will quote it later. I believe it's 6.67 times 10 to minus 34, but we'll check that later. I believe you shouldn't need to remember it though in the exam. It should come in your formula book, but I would check. So I believe it's 6.67 times 10 to minus 34. Let me just check. Yes. So it is 6.67 times 10 to the minus 34. There you go. Good. Okay, 1 second. It is in the formula book. Perfect. Good. Okay. So finally, we need to talk about the kinetic energy of an electron. So let's say I've got some electrons in my metal. And let's say I hit one of them with a photon that allows them to escape. The photon has energy h times f, but it only needs the work function, which we're going to give the symbol phi. It only needs this amount of energy to actually escape. So that amount of energy goes into escaping, and the rest is just energy that the particle now has. And so that tends to take the form of kinetic energy. So if I use even higher energy photons, the electrons which are liberated will escape the metal faster. So the kinetic energy of an electron when it is emitted is given by hf minus the energy that was needed to escape. So energy of the photon minus energy needed to escape. Good. Okay. How's everyone feeling? Does anyone have any questions? No worries. Okay, we got some ones. Well, let me know if you have. Nice. I'm always interested to see whether people choose to answer with the number or their face. Okay, well, let me know if you have any questions. In the meantime, we can do some practice ones. No, I haven't had a marshmallow and hot chocolate in ages. Right now, I'm having a black coffee, which seems more boring. Okay, so question B. A sodium metal surface is illuminated No, not the whole course here. We go through the whole course on the Stat Revise website. YouTube, we just do the occasional session. I believe I'm doing physics here once a month at the moment on YouTube. Okay, so a sodium metal surface is illuminated with incident light of frequency 9.7 times 10 to the minus 14. Now, when you're reading these questions, I would recommend labeling the quantities they give you with the symbols as they would appear in equations. It can help you kind of come up with the right equation to answer the question. Okay, so illuminated with an incident light of frequency this much, maximum kinetic energy of an emitted electron is this much. Calculate the wavelength of the incident light. Okay, so I know it's made of light. So secretly, I know it has speed c. How can I figure out the wavelength? So we saw a formula before which said the speed of a wave in general was equal to the frequency times the wavelength. Here we want the wavelength, so that's the speed divided by the frequency. This is great news because we know the speed. Good, yeah, c over f, perfect. We know the speed is this c here, 3 times 10 to the 8. And we know the frequency because they gave it here. So the frequency here is 9.7 times 10 to the power 14 hertz. So you can chuck this into a calculator and you get 3.09 times 10 to the power minus 7 meters. So it's really tiny. It's like no size you could ever imagine. Okay, so part 2. Find the energy in joules of each incident photon. So we know the light, which is made of this beam of photons, has a certain frequency. How does that give us the energy of each photon? So I should write this as energy to differentiate it from what we're looking for here. So this is the energy of a photon. We have a formula for this. It involved this Planck's constant that we were talking about. And it involved kind of the important conceptual things, what the energy depended on. And what the energy depended on was the frequency. Good, okay, so we can chuck both of these into a formula. Nice, yeah, HF, perfect. So we've got 6.67 times 10 to the minus 34 times a frequency of 9.7 times 10 to the 14. You can chuck that into a calculator and you should get 6.47 times 10 to the minus 19. Good, okay. Now we're asked to find the work function. So you're going to need to remember the formula that involved the work function, which said that the kinetic energy in the end that you get out was equal to HF minus the work function. So we're going to rearrange for the work function to find work function equals HF minus kinetic energy. Okay. Now this HF we've already calculated before. We just did it here. So 6.47 times 10 to the minus 19. What I need to know, so type it in the chat if you know which number it is what kinetic energy I should use. So here we've got 6.47 times 10 to the minus 19. And now I need to figure out how much kinetic energy this particle that's escaping sodium will have. And we're told this, the electrons that escape with at most this much energy. So we can use this as our kinetic energy. Indeed, they say it here. So 2.49 times 10 to the minus 19. Yeah, perfect. Good. Good. Okay, so you can chuck that into a calculator and you get 3.98 times 10 to the minus 19. And that's all in joules still. And finally, they ask us to find the work function in electron volts rather than in joules. So we need to know how to convert from joules to electron volts. Now we know that each electron volt was equal to 1.6 times 10 to the minus 19 joules. So if you want to find out how many electron volts you have, you just divide by that number. So the work function in electron volts is given by 3.98 times 10 to the minus 19. Good. So that's how many joules we have. And then here is how many joules there are in an electron volt. So dividing by that is going to tell us how many electron volts we have. And here we suddenly discover why we use electron volts as a unit. Because when we're talking about particles, they give us sensible numbers again. No annoying kind of powers of 10 to the 20 or to the minus 34. So this is why electron volts are a useful unit. Okay, so now some kind of more conceptual questions. When monochromatic light is incident on a particular metal plate, electrons are emitted. The intensity of light is then increased. Explain why the maximum kinetic energy of the emitted electrons does not change. Okay, so the kinetic energy is given, so let's remind ourselves of the formula first. It's given by kinetic energy equals hf minus the work function. So the point is that increasing the intensity doesn't change any of the things in this formula. So importantly, notice this says that the kinetic energy depends on the frequency, but not the intensity. So when you're thinking about intensity, which is the thing that they increased here, you can think about that in the following way. Each particle that we're sending still has the same frequency that it has before, so it will still give an electron the same amount of energy when it knocks it off. Intensity of the beam just means that there's more particles in the beam. That is essentially, if you're able to knock off electrons, you're going to knock off more per second because there's more collisions happening per second because there's more stuff in your beam. So this is a higher intensity here. So that helps us to answer the next question, which says, why is the number of electrons emitted per second increasing? So here's my plate at the bottom with all the electrons. Well, with the higher intensity beam, there's going to be more collisions per second. So there's going to be more photons hitting the plate per second, so more electrons emitted. So the intensity increase means more particles hit the plate per second, so more electrons liberated. Okay, let me know if you have any questions. Now we have one more question. So can anyone remind me in the chat what the threshold frequency was? I mentioned it informally, but can anyone have a go at defining it formally? While you're doing that, I'll read the question properly. The graph shows you how the maximum kinetic energy of electrons emitted from a surface of metal varies with frequency. So if the photons hitting the plate have more frequency, the kinetic energy you get out is more. Okay. Now explain the meaning of the term threshold frequency. So I'll fill in part of the definition. See if you can race me to it. It is the minimum frequency required to do something. But what's the something? So it's the minimum frequency required to, yeah, good. It is the minimum frequency required to liberate electrons from the metal. Good, really nice. Okay. Now we're asked to calculate the work function of the metal. Okay. So if we take a look at this graph on the left-hand side, it shows us that essentially there's no electrons being emitted until the frequency hits a certain point. And then electrons start getting emitted. With more and more kinetic energy, the more energy you put in. So this frequency here must be the threshold frequency. And the work function is just given by the energy required to liberate an electron, the minimum possible energy. So the work function here is just going to be Planck's constant times this frequency. And this frequency is 4.85 times 10 to the 14. Planck's constant was 6.67 times 10 to the minus 34. So altogether, that gives us 32.3 times 10 to the minus 20 joules. Okay, finally, they say metal A is exchanged from metal B. The work function of metal B is half that of metal A. Add a line to the graph opposite to show how the maximum kinetic energy of electrons emitted from metal B varies with frequency. So all they're looking for here is for you to know that if the work function halves, from what we are looking at here, that essentially just means the frequency needed is halved. So you're going to get the same line that they drew, but with a frequency that starts halfway in between 0 and theirs. Okay, so I now want to tell you about the other side of the coin. So the other side of the coin, rather than there being waves that behave like particles, is there's some particles that can behave a bit like waves. So let's see, in particular, some electrons behaving like waves. So a new experiment now. Now we're going to take particles and discover some wave-like behavior. So it turns out that when electrons are fired towards a thin graphite sheet, so that's what's happening here. We have an electron fired towards the thin sheet. It turns out that a ring-like pattern is formed on the detector. What we mean by that is we have a detector here. And this detector fires off whenever an electron hits it in a certain place. And what's weird is when we pass this thing through this graphite sheet, then it turns out that electrons become very likely to appear in certain places, but very unlikely to appear in some other places. Now, this is very much wave-like behavior, a kind of interference pattern between the different places it could have gone. So why is this happening? Well, it turns out graphite, you can really think of as being a bit like a grid. So it's got a load of gaps. And so there's kind of slits through which you can have interference and diffraction. So this is because the gaps in the graphite cause electrons to diffract and interfere. Okay, now diffraction and interference are things that we usually associate with waves. So the big punchline here is this means they behave like waves. Now this is important because look how we drew the electron. We didn't draw it being anything like a wave. We drew it as a blob, the particle. So this is quite a surprising scientific discovery, which we can associate some maths to. If you tell me that a particle behaves like a wave, the next question is, which wave? What's the frequency of this wave? What's the wavelength of this wave? And so this is where a new formula comes in for what we call the de Broglie wavelength of a wave. So the de Broglie wavelength of a wave, let me know in the chat, does anyone know what the de Broglie wavelength is, what the formula is for it? I'll give you a hint, which is that it can be written in terms of the mass and velocity of a particle, along with Planck's constant. Okay, so the de Broglie wavelength of a wave is the wavelength it behaves as if it has. So we agreed on the previous page that electrons behave a bit like waves. Now we want to know what's the wavelength of the wave it behaves like. So does anyone know the formula for this? So in terms of just a formula, the good news is it's quite a simple formula. It is Planck's constant divided by mass divided by velocity. So all in all, you can think about this here as just momentum. So in fact, Planck's constant is just, sorry, the de Broglie wavelength is just Planck's constant divided by momentum. Okay, so let's have a go at a quick example. I'm going to calculate the de Broglie wavelength of a 10 kilogram ball traveling at 15 meters per second. So this is a real world object, right? 10 kilograms, I can imagine holding in my hand. I mean, it's quite heavy. I'm probably not strong enough to throw it 15 meters per second, but I can at least imagine it. I guess it's a bit like a bowling ball, maybe. That's probably a bit slower. Anyway, so something a bit like a bowling ball that's moving a bit faster than usual. We're going to calculate the de Broglie wavelength. And we should, in the end of our calculation, find some reason why we usually don't have to think about a bowling ball as being a wave, because we don't, right? We think about it as a blob, a particle. And we don't seem to miss out by not thinking about it as a wave. So the de Broglie wavelength of this quite fast bowling ball is going to be Planck's constant, 6.67 times 10 to the minus 34, divided by, yeah, that's really good, Ella, yeah. Divided by the mass, which is 10, and divided by the velocity, which is 15. Perfect. So you can chuck that into a calculator, and you should get around 4.4 times 10 to the minus 36 meters. And here is the reason we don't have to care. The wavelength is so tiny that you're not able to notice it. Okay. How's everyone feeling? Does anyone have any questions? So the key thing to know from the last couple of bits is wavelength of an object, of a particle, nice, sweet, is given by Planck's constant divided by mass divided by velocity. This is the big story. Good. Okay, well, let me know if you have any questions. In the meantime, let's do some examples. So let's calculate the de Broglie wavelength of an electron traveling at 2% of the speed of light. So we saw the formula before. The thing I need to know from you guys is how do I figure out 2% of the speed of light? So the de Broglie wavelength is Planck's constant divided by mass times velocity. So that's 6.67 times 10 to the minus 34 divided by, so we need to know the mass of an electron, and you can find this in your formula book. It's 9.11. So let's draw an arrow here. 9.11 times 10 to the minus 31. Well, what's the velocity? What's the velocity of this particle? It's going at 2% of the speed of light. I think this is maybe the most awkward bit of 7i. How fast is this particle moving if it's going at 2% of the speed of light? How do I figure out 2% of something? Because I know the speed of light. Speed of light is 3 times 10 to the 8. So that's going to be in here. But how do I find 2% of it? What should I put there? I've left a gap. If I wanted to find 10% of something, I'd times it by 0.1. If I want to find 2% of something, I just have to multiply by 0.02. Okay, so you can chuck all of this stuff into a calculator. And if you do, you'll get a wavelength of 1.22 times 10 to the power minus 10 meters. Now we're asked to determine the frequency of the electromagnetic radiation that would have the same wavelength as this electron. So how do we figure out frequency? Well, frequency is given by speed over wavelength. Here we're talking about electromagnetic radiation. So not the electron that was traveling slower than the speed of light. This is radiation. This has the speed of light. But the point is, we've just calculated what wavelength it would have, which is 1.22 times 10 to the minus 10. So altogether, we have 3 times 10 to the 8 divided by 1.22 times 10 to the minus 10 meters. You can chuck that into a calculator, and you should get around 2.46 times 10 to the power 18 hertz. All right, let me know if you have any questions about that. The final questions we have are these two kind of more conceptual ones here. So this first one, can anyone answer this in the chat? What phenomenon can be used to demonstrate wave properties of electrons? So we talked about this just before we gave the formula for the wavelength of an electron or a bowling ball. But what was the phenomenon? What was the experiment? There was some kind of material. We had an electron. We had some kind of material. Good. Yeah, we had this graphite, which had a load of gaps, and it diffracted through. Perfect. So the phenomenon is the diffraction. Really nice. The diffraction of electrons through graphite. All right, perfect, good. Okay, and a final question here. Both electrons and muons were accelerated from rest by the same potential difference. Explain why they have different wavelengths. So I think there's actually quite a lot to unpack in this question. So do let me know in the chat if you have any ideas. I'll start giving some pointers. They have the same charge. Electrons and muons, but muons are heavier. In other words, their masses are bigger. Okay. So now here they have the same charge and they go through the same potential difference. So that means they have the same energy. Yeah, but they have different masses. Good. Okay. Good. So here's what's going on here. We're asked to explain why they have different wavelengths. We know they have the same energy, but the problem is the Broglie wavelength is usually given in terms of the momentum. So let's rearrange this. I'm going to tell you slightly more than you need to tell the examiner. We know that energy is a half mv squared. So in other words, mv, which is the square root of m squared v squared, is equal to the square root of, well, m squared v squared from here would be 2 times m times e. So we've got 2m e to the half. So in other words, lambda is equal to h over the square root of 2 times mass times energy. So here's a little explanation for you. They both have the same energy, as we've argued, but then they have different masses, and the masses here are now going to change what the wavelength is. So a bigger mass is going to mean a smaller wavelength. So what we need to tell them is simply the following sentences. So since muons are heavier and both have the same energy, the muons will have a lower wavelength. Okay, good. So we've covered a lot today. So you should now be able to understand how light and electrons can behave both as particles and waves. So we showed that light behaved weirdly like a beam of particles, and electrons kind of, I think, even more weirdly when going through gaps in graphite actually behave like waves. We calculated the energy of a photon, E equals hf, and the wavelength of an electron, lambda equals h over mv. And we understood how people discovered these through two experiments, electron diffraction and the photoelectric effect. So that wraps up the content that I have to show you. Do let me know as I'm going on now if you have any questions for me. I'm absolutely here to answer some questions, so let me know. Just to let you know what's coming up, we have some web classes coming up. So we have maths coming next week. Maybe a week or two after that, we have physics coming up again, and then even more maths. So do take a look. If you enjoyed this web class, there's plenty more coming on the YouTube channel. And there are plenty more web classes also happening on the Snap Revise website. Okay, so for anyone who's interested, I just want to let you know a bit now about the Snap Revise courses. So if you go onto Snap Revise with the 25% discount that I mentioned before, which we'll put again at the end, then you'll have access to the Snap Revise courses, which are actually quite a lot more than like just some revision guides or a video course. There's a lot of kind of interaction between them. There's a couple of interesting things that I want to let you know about if you're interested. So I'll just start talking about these now. Here's the code again. Now let me just take you onto the Snap Revise courses quick. So here we go. So I'm just going to show you my Snap Revise account. Now I'm in the lucky position that I have access to each of the exam boards Snap Revise courses. So let's take a look at Edexcel, and I'll show you the kind of thing we've got going on by seeing if we can find actually some wave and particle stuff to look at. So let's take a look at, say, Well, we won't take too long. So let's take a look at some stuff on longitudinal and transverse waves. Okay, so here's how the course works. You can skip the quizzes, but they're actually really useful. So they're not just to let you know how you're getting on. The main thing about these quizzes is they actually kind of shape the course around you a bit. So there's a load of video lessons that are coming, but the idea is that like the most important videos will be highlighted for you based on how well you did on the test. And the most important bits of those videos will be highlighted as well. So let's have a go at some questions. I can't promise I'll do too well because I'm going to try and rush them. The main difference between, okay, so far we're doing unreasonably well. I'll make sure to get some wrong as well, although I don't think it will be too hard. There we go. Too hard to get any wrong, that is. So, okay. Think about one more. I feel like they are, yeah, longitudinal. Okay, so the important thing will be coming once we finish this test. So, as you see, we've got an array of right and wrong answers. I'm actually getting really lucky here. I'm getting way more right than I should. Okay. So we finished our test and we've got some results. 46% correct. Absolutely great. Okay. Now we're ready to actually get started with the course. So here's kind of the good stuff. So as you can see, a couple of these videos are highlighted in green, and that essentially means that these are not high priority for me. What's high priority for me is the orange stuff. And then within the orange videos, if there was a bit that wasn't high priority for me, that would also be colored in green. So maybe we'll see an example of that here. No, we won't. Okay, so as you can see, there's lots of, here we go. So even parts of the video that I need or don't so much need to look at are highlighted here. So not only is there the video courses and actually some examples of us talking through how we would try and tackle A-level exam questions ourselves, but we're also setting up exam packs for a lot of the different topics. So for example, here you can go and see some exam questions, some kind of mock exam questions that we've been making up, and of course take a look at the solutions afterwards to see how you get on. So the point is that the course, certainly the video course at least, is supposed to kind of adapt around what you're doing well and what you're not doing, essentially so that you can kind of study smart and make sure that you're spending your time when you are revising on the things that are most effective for you. Okay, so this is what we have going on. There are also web classes. So the kind of thing I've been doing today, I do a few of these a week, and all in all, there are, I believe, 4 or maybe 5 physics sessions a week of the type that I just gave here. Some of them are sessions where we just talk through some material like I did today, and some are more like drop-ins where you can come in with any questions that you have and ask about them. But that is a separate thing, as like a tutoring service, if you like. So the discount that we have today is for the courses service, so all the things that I've been demonstrating on my screen here. So it'd be really good to see some of you over there. And do let me know if you have any questions about all of that stuff. In the meantime, let me take you back to the screen. And you can see, so I mentioned the smart quizzes. We also have condensed revision guides that we've been setting up. And here is the, oh, I'm using the wrong arrow. Here is the discount code for all of that stuff on the previous page. Okay, so let me know if you have any questions. I'll just take a look at the chat. Easier way to understand particle physics. Yeah, I would say it's pretty broad, sadly. It's kind of, I guess I don't know which books you're necessarily using. But I think I can't off the bat give too much advice there. Okay, so as I mentioned, oh, no worries. Cheers for coming. And thanks everyone for putting all your thoughts in the chat. It's really useful because it helps me to figure out how you're getting on with this stuff. So yeah, thanks very much for coming, everyone. And I'm actually going to go now give a web class on the Snapvise website. So I will have to make a move there. And yeah, thanks very much everyone for coming, and catch you next time. All right, bye.